Hi everyone. In this video we are going to look at the concept of calorimetry again in the context of measuring the heats of chemical reactions. From our discussions in earlier chapters, we know that calorimetry is the measure of heat flow in or out of a system. And we can calculate heat flow by the equation Q equals mCs delta T. So if we know how much mass of a substance, how much the heat capacity is, and the change in temperature, we know how much heat has been absorbed or released by that substance. And this was applied to various substances during warming or cooling of pure samples, right? So let's review what each term means. Q is the heat, right? Typically in joules or kilojoules, depending on the magnitude of the number. We have CS as the specific heat, and specific heat is in joules per gram degrees Celsius or joules per gram Kelvin. And note again that we're talking about a change in temperature, so whether that changes in degrees Celsius or Kelvin, it does not matter because the change in Celsius is the same as the change in Kelvin. So we'll just write that out. Delta T in degrees Celsius is equal to delta T in Kelvin. So you don't need to do your unit conversion there. M is the mass, and this is the total mass of solution. Right? And then delta T is the change in temperature, which can be calculated TF minus TI. And for water, the specific heat, which is most of the time the liquid that we're going to be dealing with, the specific heat for water is, for liquid water, 4.18 joules per gram degrees Celsius. Okay, so that's a number that would need to be provided for you for these types of problems. Okay, now, when we are talking about calorimetry, we're often talking about measuring the change in temperature of a solution in what we call a coffee cup calorimeter. So this is my thermometer, and we have some solution in here where a chemical reaction is taking place. The reaction takes place here. And we have to remember to differentiate the system, the chemical reaction that I'm studying, versus the surroundings, everything else. So the chemical reaction is taking place within this solvent, and so that solvent then would be defined as the surroundings. So that's something very important. Solvent is the surroundings. And typically, often, for us at least, this will be the water. And we can measure the temperature of the water more easily than we can measure the temperature of individual atoms taking place, reacting in this chemical reaction. So that's what we see. We can calculate Q of the surroundings by mCs delta T, and then by the first law of thermodynamics that says energy is neither created nor destroyed, simply transferred. We know that the Q surroundings is equal to negative Q system. And therefore, if I have a positive Q of surroundings, meaning the surroundings gained heat, we know that the reaction itself then will have a negative sign, it will have been exothermic, and will have lost the heat. Okay? So let's look at an example. Let's say we have a scenario where a student in the lab is mixing 50 milliliters of a 1 molar NaOH solution and 50 milliliters of a 1 molar HCl solution in a coffee cup calorimeter. So we have this coffee cup system that isolates and insulates our reaction mixture. So we pour our solutions together, the sodium hydroxide and HCl will react together. That's my system, the chemical reaction that we're studying. And then the water itself is the surroundings, that solvent. and we can measure the temperature change of that. The student measured a temperature increase from 21 degrees Celsius to 27.5 degrees Celsius. So can you take a second and predict whether the reaction was exothermic or endothermic, and what statements here are true? From the equation, Q is equal to mCs delta T. If we're measuring the temperature of the water, and that's the surroundings, delta T will be positive because the temperature increased. The final temperature will be higher than my initial temperature. So Q surroundings will be positive, and since Q surroundings equals minus Q of the system, the Q system will equal negative Q surroundings. So we'll have a negative sign in front of my number, indicating that the reaction is exothermic. Okay, so exothermic reactions mean that heat was released from that chemical reaction. The energy of my products is lower than that of my reactants. So if we're thinking about a reaction coordinate diagram where I have reactants and products, they would be at some lower energy. So delta H here is going to be less than 0. And this is H on the y-axis, and this is the reaction coordinate, which is kind of arbitrary, just saying the reaction progress with respect to time there. Now, let's say we want to do more with this information, more with this data that student collected. Let's say we want to calculate delta H of the reaction in kilojoules per mole of HCl. Okay? Now, assuming that the calorimeter loses a negligible amount of heat, and the total volume of solution is 100 mils, and given a density and specific heat. So, there are some steps to this type of problem. We need to, one, find out how much heat is generated for that specific reaction mixture, right? We used 50 mils and 50 mils of the 1 molar solutions. How much heat is given off when those quantities are mixed? Then we kind of need to normalize that to per mole of HCl. The first step was that we're going to calculate the heat exchanged in this reaction. And we know that it's exothermic, so we know the heat is released, all right? So Q is equal to mCs delta T, and we have 100 milliliters of solution, and the density is 1 gram per mil, so my mass is 100 grams, all right? The heat capacity was given as 4.18 joules per gram degrees Celsius, and my delta T is going from 21.0 to 27.5 degrees Celsius, so delta T is 6.5 degrees Celsius. So my units cancel. I'm left with an energy unit, which is great. So I get a positive 2,717 joules of heat released in this particular reaction. We know from this that Q surroundings equals negative Q system. So if I have plus 2717, this is going to equal minus 2717 joules for the system. Okay? And that's not my final answer because this is joules per however many moles of HCl reacted in that reaction, right? We didn't use 1 mole, which is what we want, kilojoules per 1 mole of HCl. We used an unknown at this point number of moles. So we need to find that. We need to find number of moles of our reactant. And the reactant that we want to know is HCl. So we're going to find the moles of HCl. We have our reaction that we'll need to balance, NaOH plus HCl. That would be a double displacement. We'd swap the metal and the hydrogen to give water and NaCl. The driving force for this reaction would be the formation of that non-electrolyte water. And balancing it is already taken care of. This is a strong base, strong acid reaction, so it reacts 1-to-1 and gives water and NaCl. So we need some more space, so let me erase. Okay, so we need to write down the information. We're reacting 1 molar solutions, 50 mils of each, and we're on our way to find moles of HCl that were used in this reaction. So we would convert moles per liter rather, to a moles, 0.050 liters, and that gives me 0.05 moles of NaOH, and the same calculation would hold true for HCl. So this is 0.05 moles, 0.05 moles, okay? And then from here, step 3 here would be determine delta H reaction in kilojoules per mole of HCl. So we need to take the kilojoules, so Q is equal to minus 2717 joules, and divide that by how many moles of HCl reacted, 0.05 moles of HCl, and gives me a number of minus 54.3 kilojoules per mole. So this is the way of normalizing the heat of reaction, okay? Now, there is a convention here where we typically will write the heat of reaction next to the balanced chemical equation and say, well, delta H of the reaction is minus 54.3 kilojoules. And so we're missing that mole unit. So it's implied that this is kilojoules per some number of moles in the balanced chemical reaction. So this is kilojoules per 1 mole of NaOH. I could write it like that. So minus 54.3 kilojoules per 1 mole of NaOH. Or I could write minus 54.3 kilojoules per 1 mole of HCl. Or I could write minus 54.3 kilojoules per 1 mole of water produced. And these ratios, these definitions, can be used in other types of problems. Say, if I know the heat of reaction, well, how much heat am I going to get if I react 10 grams of this? 10 grams may not be 1 full mole. So I can use this relationship and figure out how much of a particular, how much energy a particular amount of substance will release. Okay? So this can be used as a unit conversion factor in those types of problems. We'll look at another example in the next video, so stay tuned for that, and thanks for watching.